So first of all, thank you for inviting me to give this talk regarding our new paper, Unveiling the Potential of Graph Neural Networks for Robust Intrusion Detection. So in recent years, it has become a reality that our lives are increasingly dependent on the use of the internet, basically for any application that we use. But this, of course, has important challenges, and perhaps one of the most important ones is cybersecurity. In this regard, for example, in this plot, we can observe that the number of malware infections has grown drastically throughout the last decade. And this not only has a major impact in the economy, for example, it's over $100 billion yearly in the US alone, but it also poses a threat in the user's privacy because of data breaches. In this regard, one of the techniques that has gained lots of attraction so as to mitigate this problem is the use of intrusion detection systems. And basically, an intrusion detection system would really consist of is a system that tries to detect whether the incoming traffic is malware or it's benign traffic, and thus should be permitted. So at the end, what we end up facing is a classification task on the incoming traffic that we receive from the internet. And one may ask, how do we approach this problem? Well, in recent years, like any field in technology, really, the rise of machine learning has caused a lot of novelties in this aspect, and many proposals have approached it through the use of traditional machine learning methods. For example, MLPs, support vector machines, random forests, etc. There is, however, a major limitation, and this is something we argue in this paper, of using these techniques, which is that they normally rely on considering the flows independently. And this is, of course, a major simplification from the real world scenario where we can have a multi-flow attacks. So let me be a little bit more concrete. For example, one of these IDS, for instance, would receive several flows, let's say 3 flows. Then it would obtain the features of each of these flows, and then it would progressively pass these features, say, for example, flow 1, through the trained machine learning classifier. And with this information alone, it would try to predict whether, for example, flow 1 is a DDoS or not. But again, this may not be sufficient information. And in fact, let me just provide one simple example to illustrate that. Let's take this real scenario where we can have a port scan attack. So basically, in a port scan, we have numerous port scan queries being done simultaneously in a computer. So what an IDS would do is that it would just simplify it and just consider one single port scan at once. And the question that one may ask is whether this is enough information to decide whether this is an attack or this is just a normal application doing a port scan, which is routinary. And the answer is that this is technically impossible. We don't really have enough information to decide that. And this is precisely the motivation for using more complex IDS as the one we propose in our paper. And in these more complex techniques, what we need is to consider many flows simultaneously. So what we gain by considering multi-flow simultaneously is, at the end, we are expanding a little bit our knowledge of the current network, which has an obvious benefit in multi-flow attacks. One way to do this modeling of the incoming traffic is by modeling through a graph, which turns out to be very natural, as we will see. Here, for example, we show a way to model the incoming traffic as a graph. And the interesting properties that we found while trying to model it is that we noticed that we ended up with attack characteristic patterns. So for example, observe here, we can see that the pattern that we obtain from the DDoS attacks is completely different from the port scan or network scan. And this is, of course, extremely valuable when it comes to learning algorithms. Another important property that we found is that these graphs, are invariant to the features. So in this case, for example, and we'll talk about it later, these graph nodes represent connections. So flow 1, for example. In this case, what we saw is that even if we change the features of, say, flow 1 for whatever reason, a change of the network, for example, this graph structure would remain the same. And as we will see, this turns out to be crucial to build a model that is robust to network changes and, for example, to adversarial attacks. One may ask how we can learn from these models that from this graph that we obtained through modeling the input traffic. Of course, the first thing that comes to mind is the use of artificial neural networks. And in fact, it has been tried in the literature, but turns out that the artificial neural networks are not well suited for graph structure data. The main reason is that they require to have a fixed size input. And this is, of course, something we cannot guarantee in this scenario. So this is why we propose to use graph neural networks. Graph neural networks turn out to be extremely adaptable in these scenarios. So they are able to support throughout the same training and without making any change, graphs of different topologies with different nodes and edges. And this is done basically because the architecture of the GNN, as I will explain now, is built on the fly, really, and it depends on each of the graphs that we feed it with. Another of the reasons is that it generalizes well to unseen graphs, which of course motivates the use of GNNs. And in fact, this has been shown in other fields such as computer networks or power networks. So let me go a little bit through what a graph neural network is. First of all, let me mention that there are many types of GNNs, graph neural networks, but I'm just going to talk about the message passing neural network, which arguably is the most general framework. And also that the basic idea of the GNN is that it does not try to learn from the whole graph on its own, but it just tries to learn these relational patterns within the graph, which, as you may recall, is really what we care to find these patterns that identify each of the attacks. And again, this is done by using neural networks and connecting them according to the graph topology. Going briefly through the formulation for sake of completeness, let us take, for example, this very simple case with 3 nodes. So the first thing that a message passing neural network would do is create the hidden states for each of the nodes, which are just real values vectors, where we encode the features. So if this is a connection, we could encode the protocol, we could encode the bit rate, or any feature that is relevant. Then each of the nodes sends a message to the neighbors. So for example, V2 would send a message to V1 and to V3. And concretely, for V2 to send a message to V1, it would use a neural network, and it would pass it its current hidden state and the hidden state of the destination. And with that, we could generate the message that we want to send. The second phase would be that once each of the nodes has all the messages from all the neighbors, so in this case, from V1 and V3, they just aggregate it together into one single embedding, for example, through a sum. And finally, they update its current hidden state accordingly. So taking this new embedding that they received from the neighbors and taking its current hidden state, they would use a neural network to predict its next hidden state. Finally, this process is repeated T times so as to obtain more information. Finally, we have the readout function, which just uses the final embeddings that this process produces so as to make the prediction of the model, which of course depends a lot on the problem that we are treating. But I'm going to give an example later. This is just a simple illustration that illustrates how a GNN at the end is just a smart way to connect a series of neural networks according to the graph topology, which is why a GNN is so flexible in this sense. But what is exactly what we propose in this model? Well, what we attempted to do, and I think we accomplished it, is to build a GNN-based IDS. And of course, the first thing that we need to do is to go into details on how we build the graph, how we model the incoming traffic. And what we did is we proposed the use of what we call the host connection graph. And the host connection graph is really, well, I'm just going to give an example which might illustrate it. Let's take, for example, this case with 3 flows. What we do, first of all, is to create this one node for each of the different source IP and destination IP, which in this case would be these light blue nodes. And then we create one node for each of the flows. So in this case, one node for F1, one for F2, and one for F3. Finally, we connect these nodes according to the message, to the traffic that we received. So, for example, connecting such that this IP created this flow, and this flow was received by this IP. So this way, we end up transforming all the flows that we received into a graph. Then we trained our graph neural network, which is based on the standard message passing formulation that I described before. Of course, one may notice that now the graph that we are dealing with is no longer homogeneous, but rather heterogeneous, because we have nodes that represent IPs and nodes that represent connections. But we found that we did not need to make such a big distinction. So at the end, we could just apply the same formulation that we saw. And at the end, each of the nodes sends the message without worrying what the specific type of node it represents. And of course, after this message passing phase, we notice that at the end, what we want to do is to make a prediction on each of the connection nodes. So for example, we want to know which type of attack the yellow connection represents and which type of attack, if any, the green connection represents. So what we propose is to use the final hidden state, say for example, of this connection, and then pass it through an MLP model, which at the end predicts the type of attack that it represents. Then we can go through the experimentation, and here, in fact, we provide the results of the experimentation we did on the IDS 2017 dataset. And here what we can observe is that our proposal obtains state-of-the-art results in basically all the attacks compared to representative machine learning-based IDS. What was surprising to us is that here we can observe that random forest and IT3, which is a tree-based algorithm, quite simple in fact, obtain perfect accuracy almost, even in, for example, the setting of the port scan, which we already discussed, which was surprising because random forest at the end considers flows individually. So again, this is counterintuitive because what we already explained. So our hypothesis was that these algorithms performed very well, but not because they were really understanding and capturing what a port scan, say, is and how it behaves, but rather they were just capturing characteristics of the specific data sets. So they were overfitting on the data set that we were testing it with. And this is in fact an important limitation, because if they are overfitting to the data set, they could, for instance, not work when we tried with a different network with different feature properties. This is something we tried to test, and to test it, we devised two simple adversarial attacks. The first of all was to increase the packet size of our connections progressively, as we show here. And the second one is to increase the inter-arrival time. And these are, in fact, the x-axis in these plots, and the y-axis are the weighted F1 scores. Here, if you observe, the results are very similar. What we can observe is that our proposal basically maintains the performance throughout the experiment, even if we change these features. Meanwhile, the rest of the models do not adapt as well as we do, and the performance degrade. This, at the end, what tells us, and the conclusion that we extract, is that our model no longer only depends on the features that we fit it with, but it also somehow relies in the structural patterns that we were discussing before. So it's extracting patterns from the graph that are invariant from the features, so that we can change the features and our model does not seem to be affected by it. Sorry. Finally, let me just conclude that in this paper, we try to motivate why it is important to use graph-based models to model graphs to model the incoming traffic with respect to naive approaches. Also, we observed that using a graph neural network-based IDS, our model was able to capture complex graph structural properties of the graph, and thus it does no longer depend only on the features that we fit it with. And finally, that our model with these properties not only obtains state-of-the-art performance, but also is able to be robust to adversarial attacks, unlike the benchmarks we tested with. Finally, for the interest of the audience, let me just provide that we some information. We used this framework for graph neural networks called Ignition, which basically allowed us to model our GNN without using TensorFlow or PyTorch. And also a graph neural networking challenge that we are organizing to further explore the potential of GNNs in other domains, such as computer networks. And I think this is it. Feel free to ask me any question or doubt that you may have. Thank you.
Thank you, David, for the talk. I found really interesting, especially also informative, the part and the discussion interpretation about why you should treat you shouldn't treat independently the different flows. So very didactic also your talk.
Thank you.
And well, I do have a question, then first question, then I will also see if the other people in the audience have others. So you showed the robustness with respect to two features in one of the last slides. So why did you choose these two features to check the robustness against, or you also try with other features and you just show these two like randomly?
This is a very good question, and this is in fact future work. So at the beginning, we wanted to test it with the simplest adversarial attack that we wanted to come up with to see to what extent the baseline, so in this case, random forex, for example, or ID3, were robust to these changes. And really, these were the experiments the simplest experiments that we could come up. And really, we were surprised to see such a big influence of these adversarial attacks. Regarding other possible experiments, I have to say that this is future work. And one of the things that we are now very interested in is on devising more complex adversarial attacks that no longer depend on one single feature, for example, or that have more complex properties to see how our model and how the other models behave. But this is definitely future work that we're planning to work on.
I will look forward to it. So are there other questions for David? It seems no, so thank you again.